A couple of things with stepper motors today. Well, we're going to look inside a stepper motor, and a lot of the calibrations that we will do have to deal with stepper motors, so we'll look at those. I got a couple of our print and paint type stuff done, a little bit anyway, not a lot, and then just some tune-up type things. So a lot of things since we changed the firmware over to the Marlin 2.0 when we changed the board, they aren't in tune anymore. It has whatever was built into the profile that we loaded onto it, the firmware that we loaded onto it, and it wasn't necessarily tuned to our printer. So there's a couple of things that we need to go through and check on, make sure they're okay, or if they're not okay, then we need to fix them. We won't do all of them today, but some of them. First, let's look at some of the printing and painting type things. So let's get these out of the way. I never found the chrome pen, so I just bought another one. But this is what I was talking about, is this liquid chrome pen. They come in pen. You can get just the ink refills, so if you wanted to paint them on with a paintbrush or even an airbrush, I haven't tried that, but they do have refills of just the ink if you don't want the pen part. This is the 2mm version. They have different ones with different size nibs on them. This one seems to be generally good for what I'm going to do with it. And it's just a paint pen, right? So this is one of the scope rings for our little blaster we've been working on. And this is what I was talking about. It looks a lot like, if not chrome, really shiny polished metal. Although it kind of has that thick chrome, like chrome on top of plastic look to it. I don't know if it has a particularly like chrome on top of metal look, but it's really, really close. It's closer than anything that I know of other than some expensive products that you're going to just be able to spray on. And this one's even easier, you just paint it on. So I thought I'd show you what it looks like. Here's the other scope ring. And you literally just paint it on there. You kind of let it get thick, and it will level itself out after a while. But this is all I did to the other one. And I probably should have shaken this up. I didn't even do that. Probably should though. I didn't even think that it might have settled out. But that's all you do. Like, you can do the sides too if you want to. I'll do those later. And I didn't do the insides in here apparently. But it works really well if you're trying to make some kind of chrome-like or highly polished metal-looking surface. I didn't even prime this thing. This is straight off of, this is one from the resin printer, so it's a little bit smoother surface to begin with. If you were doing this on a FDM, like the kind of print that we've been doing, you probably would need some surface prep, because it will flow out and fill in the surface. You can kind of see this one's already begun to flow out a little bit. It's still a little lumpy though. But it probably would pick up a lot of these layer lines and not quite look as good. So it does look better over a flat surface. It would generally, these things, now this one's pretty thick, but these things look better over a gloss black if you're trying to get a really highly reflective chrome look. I didn't bother with this one. I just painted it straight on top of the green plastic, or resin. It's not necessarily plastic. So I did that. I worked on these a little bit. Basically, I sanded and sprayed the adhesion promoter, and then a coat of Duplicolor sandable primer. So it's a little bit thicker primer. And I think probably I may sand this a little bit and then get to work making this look wooden, because this is supposed to be a wooden piece. And that's all I did on the blaster painting. Didn't paint anymore, or didn't even make any more of the little miniature guys. I think we're done with those for now anyway, at least for the class. But I thought there's still a couple more things. I did buy, we did the rub and buff on the flash suppressor. Let me get it. This guy. You can also kind of see the difference in this chrome finish versus the rub and buff. So over the This one is shinier. I don't know how well it shows up on the camera, but this one is certainly more reflective. And I didn't do any prep underneath it either, so I probably could have gotten a smoother surface to get this even more reflective. This one is certainly not that reflective. It does have kind of a metallic look to it. I found that they make an ebony rub and buff. So I ordered that. I don't know when it'll come in. They didn't have anywhere other than, I think I got it off of Amazon. No, I got it off of Hobby Lobby's website. I looked on Amazon, so they didn't have it. And anyway, I'm going to use that on top of this to kind of make it a little darker in some places. Hadn't come in yet, so that's about all I did on that. Another project that I started, got lots of started projects. Let's get these out of the way before I do something to mess them up, though. Put it over here. Another thing I started was wanting to make a birdhouse. Actually, my boys wanted to make a birdhouse. I didn't particularly myself want to make one, but that's what they wanted to do. And so I started printing one, and on the suggested settings in it came from Thingiverse, so the suggested set is there that the author of the birdhouse said worked well. One thing that it said was to use one wall and 2 top and bottom layers and a relatively low infill, like 10%. So I did exactly what they said, and this is what I got. It completed the print, so that's not the problem. The problem is you get these little spots. Let's see if we can focus better. Well, I think you can still see them there. So all of these little gaps right here around the part, so it sticks out, right? So the word bird sticks out, and there's the hole for the bird to go in. But you got a flat surface, and then stuff walls that are vertical walls on top of that flat surface, and there's all these gaps here, and it's all around. It's around the whole thing. So what's causing this is, and I'll let it finish the print because I wanted to show, because sometimes this is a thing that it worked on one printer or one person's profile, and yours is doing this kind of stuff. So you have to try and figure out why is it doing what it's doing. So I happen to know why it's doing this, but so it'd be tougher if you didn't see it before. But if you saw it while it was printing, you would see, and you might even be able to pick up, I don't know if you can see the layer line, the infill lines, you might be able to see their shadows kind of in here. Basically, it's got a rectilinear infill, so it looks like a bunch of diamonds in here. And basically, every one of these ends where there's a row of infill. So, you know, the way it would work, it is hollow on the inside. So it would work by printing this top layer. Now there's only 2 top layers also. One wall, so one wall here, yeah, you can see that. There's one wall and 2 top layers with this relatively light infill. And when it goes to print this top surface, it should attach the top surface to that wall. But instead, it would drive over there, get really close, and then the head would move away before, you know, it actually adhered to the wall here. And the filament would just kind of fold back on itself or droop down into the print, or melt and curl up, and it leaves these little gaps, and you can kind of tell that they match this pattern of infill. The infill is going this way and this way, and you can kind of see how they match that pattern. So a couple of ways to fix this. One would be more walls. One would be more top layers. Another way would be you can actually specify the amount of overlap between where you meet a wall. Overlap, maybe it's wall overlap or something like that is the wording for the setting. But there's a percent. It's usually given as a percent. And I think the default for this particular printer was 15%. So maybe you go up to 20 or 25% overlap, and it will do a better job of making sure that these top layers are stuck to the wall. So the first time I went to fix it, I just decided I'll do 2 walls. So this one is with 2 walls. If you can't can't really see the two walls here. Maybe you can pick them up, but there are two walls compared to one wall on this one. You can kind of see the two different lines right there and there. And it's better, but there is still some gaps. There are still some gaps. There's one inside there. And so it's still having trouble adhering the top layers, and it still only has two top layers here, to the wall. So this was just increasing the number of walls from 1 to 2. I don't think I even increased the infill. No, that looks like the same infill pattern, so still 10% infill. It did get better. You can see here's the one wall. Actually, right there you can see the wall. It didn't even stick to it. And then here you've got fewer, but they still exist. Let's look at the eye on both of them. It's one of the worst ones. If I can get them, I might have to zoom out. So there's the kind of side by side. Two walls, one wall. Not completely cured, but better. Then I said, well, let's just go back to the settings I normally use. I normally use 3 walls. I normally use 2 or 3, maybe even 4 top and bottom layers. Now this thing's pretty thin, so if I use 4 layers top and bottom, it's basically solid at that point. So I think I did 3 layers of top and bottom, which will also help with this type of thing because it gives it more chances. It's going to come at it one way, come at it again from another direction, and then come at it again for the 3rd layer. And you know, between those 3 layers, they probably will actually adhere and stick on that top final surface. So I did that, and I increased the overlap percentage to 20. It was 15. So the final one is this guy. And now I did introduce some new problems, like there's some ghosting going on here. You can kind of see the shape of this B gets ghosted in here, and then kind of several other places that exists, but there are no gaps anymore. So 3 walls, and you know, normally if you're trying to experiment and figure out the ideal settings, you only change one thing at a time. I changed 2 or 3 things at a time, so I don't know which one is the one that better solves the problem, but those 3 things work together to solve the problem. Just adding more walls is a big part of solving the problem, but you might need to add more walls and increase that overlap, or add more top layers and more walls or whatever. But I know that this problem shows up several times, and it's hard to track down what causes it because you don't even think about it's printing correctly. And you look in the slicer, make sure there's no holes in the slicer like this, that it didn't somehow slice it with these holes, and it doesn't. And a lot of times it's something where you're trying to speed up the process. You know, the walls take a longer time to print because they're slower, and so maybe you drop down the number of walls, or maybe you drop down the number of top layers or bottom layers, just trying to speed up a long print. Now this isn't a particularly long print. I think it's 2 hours or so, so it's not terribly long anyway. But you can also see, maybe you can pick it up. I don't know. Yeah, you can see in the dot here for the eye. See those little bumps? That's called pillowing, like a little pillow on your bed or whatever. But those little bumps, that's usually because you don't have enough top layers. So that goes away when you add more top layers, and you don't have those little wavy bumps on the top down up across the surface. Particularly happens on flat surfaces. Another thing you can do to reduce this is increase the infill percentage so that there's more areas for the material on that top layer to stick down to. A lot of it also has to do with cooling. You know, not cooling fast enough, it stays molten longer and it droops, and it as it cools, it will change shape, and it creates these little pillows on top of stuff. So I just thought I'd show you those because you might run into that and not know how to fix it. If you know the right words or can describe it well, generally you can find on the internet someone else who's described this problem and solved it. You just have to be able to describe it the same way that they thought of describing it. So this surface up here is called pillowing, and these are generally just gaps in the surface, gaps in the top surface, stuff like, I don't know exactly if they have a terminology, but they're due to the top surface not sticking to the wall here that makes the B or the I or the D or whatever's there that you're trying to stick them to. So cooling, more increasing the walls, printing slower can even solve that too a little bit. I was printing relatively fast to try and speed up, you know, a bigger print. So I want to show you those. Let's see, what other things before we get into the, I think let's go over to the printer and let's talk about stepper motors. So these stepper motors are pretty typical of what's going to be on a 3D printer like the ones that we've been working with. This one actually came off of a TiVo, but it's the same exact type of stepper motor that you'll find on the Ender 3 and other printers like that. It's called a NEMA 17. So let's see if I can find something to write with. Whoops, we're off the screen. Where's the screen? There we go. NEMA 17. The 17 and the NEMA, what those are describing is basically this front plate and the bolt pattern right here. That's all it really describes. So it doesn't describe anything about the strength of the motor or the way it works or anything other than it describes how you mount it to something. It doesn't even describe how long the motor is. You can have a NEMA 17 that's this long or a shorter one or a longer one, and it's still a NEMA 17. So you can't just necessarily go buy a NEMA 17 motor to replace a burned out one on your printer, because NEMA 17 means that it just has this bolt pattern on the, and this, I think it also might describe this particular shape here, but it's really this bolt pattern is what it's describing. So you do have to make sure that you have the right type of NEMA 17 motor. This one was off of an extruder. It's got a gear. Oh, this might not. I wanted to take this one apart. Let's see if we can get it apart. It might create problems because it's got this, I think it's just kind of a plastic gear on there though for the extruder. But let's see. I may have to go find another one if I can't get it off past that gear. Or we might have to just figure out how to get that gear off of there. But there's four, generally four. I've never seen one with other sizes or numbers of screws in the back, but there could be. All right, so these screws basically go all the way through and hold it together. Let's see if I can get it to come apart from there now. Wow. May have to get some more tools here. It's really holding itself together. And I can't remember. So the way these plates, from what I remember, are totally separate. And this center part in here is a stack. And you can kind of see how it has little lines in it. It's a stack of plates. Now they're usually not something that's going to come apart. But let's see if we can, I might have to go back here to the bench to pull this thing apart. All right, I just took and basically did this, tapped on it. It didn't take a lot, I just had to get it started so that we can pull it apart. Now it's tough to pull apart because the center part is a permanent magnet, several permanent magnets actually. So there we go. So let's see what we got in there. These here are, let's zoom in because there's some details on them that you need to know about. Or, well, you don't need to know any of this stuff. It just kind of is useful to know. These are permanent magnets. This part is the rotor. It rotates. And obviously it's connected to whatever your output is. So either a little pulley or a gear, depending on what you're trying to drive. And if you look close at this, these are two separate, now they're actually magnetic, see? But they have these little teeth. These are also stacks of metal. You can kind of even see how they're stacked together there. And look how the teeth line up. The teeth on one of these sections is a North Pole magnet, and one of them is a South Pole magnet. I don't know which was which. I assume it's kind of standard. I just don't remember which is which. But one of these is north, and one of these is south. And they are lined up so that the little teeth inside here, I believe there's 50 teeth all the way around. I'm not going to count them, but I believe there's 50. And the ridges here line up with the valleys on the next piece, all the way around. So that you have, they're offset from each other perfectly, so that the ridges on one line up with the valleys on the other. And one is a North Pole, one is a South Pole. Inside here, these are permanent, so these are permanent magnets. Inside here, you can kind of see the windings. These are electromagnets, so they're not permanently magnetic. And they can be turned on and off to create a magnetic field. Now, it looks like there's a whole bunch in here, but there's only 4 wires most of your printers anyway, if you ever looked at it. There's actually 6 plugs on here usually. Yeah, 6 plugs, but only 4 wires that go to it. So how they've got this wired up is these are wired in phases or pairs. So I don't know which are wired to which set of wires, but these two are wired together, and then these two are wired on that same setup but backwards. So if these are creating a North Pole magnetic field, these are creating a South Pole magnetic field. And so maybe that's the I don't know what color wires are coming off of these things. I can't even see any of mine right now to see where the wires. So they have, actually on the ender, how many wires do they have? They have 4. Yes. Oh, well, they're just all black wires, so you can't tell what's what. A lot of times they're colored like red and yellow and green and blue or something. And so 2 of those will be paired together. So 2 wires would control these 2 and these 2. The other 2 wires would control these 2 and these 2. And inside here, they have ridges inside associated with each set of coils. So there's 1, 2, 3, 4, 5, 6 ridges per coil, and there are 1, 2, 3, 4, 5, 6, 7, 8 coils. So there's 48 little ridges in here. There are 50 little ridges on each one of these rotors. Rotors. These are the rotors. This part it's stuck to it. This part in here is the stator. It's stationary. These rotate. So there's a different number of ridges between the rotor and what's inside here on the stator, so that they don't line up perfectly. If you could get it in there and every little ridge here matched up with a ridge in here, it would move to that spot basically and stay there, and you wouldn't have a way to move it around. So there's a little tiny bit of offset. You can get one little set of ridges lined up with 1 or 2 of these. I think maybe 2 at a time. So if you're lined up with these 2, then you're off a little bit on all of these 2. So if you're perfectly lined up here with the ridges, then these are probably lined up with their ridge is lined up with the valley over here. And then these are offset a little bit so that there's a little bit of, you can change which set of these is active or which set is north and south, and it'll rotate 1 step. So they're called stepper motors, and this distance between the ridges defines the step. So by default, this one is a 200 step per revolution motor. There's 50 here, and there are 4 positions that it can line up ridges with ridges here. It can line them up here. That's 1, 2, 3, and 4, and then it's back to where it started. So you can get 200 steps out of one of these type stepper motors. If you divide 360 degrees by 200 steps, the stepper motor can hold 1.8 degree increments. So it can go 1.8 degrees in what's called a full step. Now, these stepper motors, that wouldn't really be enough. 1.8 degrees sounds really small, like a small increment, but a lot of times you're trying to print something that has resolution smaller than that. So you'd either have to gear it somehow, so put gears on here to make this step even smaller, or do some trickery inside here. And so they decided to do some trickery inside here. Generally, gears are not the thing you want to do in a high resolution machine because of what's called backlash. So there's a little bit of give between a gear tooth and its mating gear tooth. And when you go one way, it's fine, but as soon as you need to reverse direction, there's a little bit of backlash. So the gear turns a little bit, or actually the pinion turns a little bit before the gear starts moving. And so gear trains are generally not something you want in something that you want to be very high precision. So instead, what they do is they go over here, and instead of thinking of only allowing the rotor to move to these 4 different positions inside here, or the 200 different, but the 4 sets of magnets, it's possible to say, well, if I give some power to both sets here, then I can kind of make it exist between steps. So that's called micro stepping. And well, actually that would be called half stepping if you did where it's, if I energize this coil 100% and this coil 100%, then it would be right in the middle of those two. So that's a half a step. And I could do the same thing down to a quarter stepping, an 8th stepping, 16th, and 32nd, and it keeps going. The board that we have in here, I don't remember, it can do something like 101 over 256 steppings or whatever. It's a super tiny amount of steps. Now, the problem does arise that at some point it just gets difficult to accurately resolve or hold those steps when you have every coil energized to exactly the right amount of current so that it's producing just enough magnetic field to get your rotor to whatever position you're trying to get in. So it's not always practical to do super tiny micro steps, but that's one way that you can get higher resolution out of a motor like this. So I just wanted to kind of give you an idea of what's inside here. Electromagnets that you can turn on and off selectively that will drive permanent magnets to certain positions. And that's really all it is to it. And then you put it back together, screw it back together, and you've got a stepper motor again. There are different types of stepper motors. This isn't the only type. This one's called a hybrid. So it's using two, kind of the benefits of two different stepper motors that we didn't really talk about because they're not what's used in a 3D printer. But don't be afraid of them. And look, you can take it apart pretty easily if you want to go in there and look and see what's going on. You just have to have a general understanding of what a step means. But a step in a stepper motor is one of those positions in here. And the difference here, this is still DC direct current motor. So I'm applying the same kind of power that I'm applied to a little, well, the motor inside here even. Same type of thing. The motor inside here is not a stepper motor, it's just a DC motor that I can make it go different directions and different speeds. But here I can go different directions, different speeds, and I can go specific amounts. That's the difference, is I can tell it to take 30 steps in one direction or 20 steps in the other direction. And as long as it hasn't skipped one of those steps, so I haven't tried to make it go too fast or put too much torque that it had to deliver, then I can be pretty sure that it actually went exactly that far. Now, there is no feedback, so the machine doesn't know if I tell it to go 30 steps in one direction, it doesn't know if it actually did that or not. There are some add-ons. They're actually not that expensive, maybe $20, that you can add on here that is basically an encoder that tracks, did this thing actually turn 30 steps or not when you told it to? And if it didn't, then it can compensate for that. It can say, you skipped 10 of those steps, go do 10 more steps. So you can add those on. If I was going to add one, I would probably just add it to the the bed on an Ender 3, because it's the one that's most likely to skip a step. I have not ever actually added one of those on there, though, to take advantage of that. Generally, what you do, if you see layer shifts, so you're printing along fine, and then everything moves over by a certain amount, it doesn't matter what the amount is, it just shifts over and prints some more, but there's this shift in your print, your stepper motor has skipped some steps. Because it doesn't know where it actually went. It just knows where you told it to go, and it tried to go there. It tried to take 30 steps, maybe it only took 20. Or maybe usually it's not going to take an extra step. It's usually going to be less steps than what it was intended to take. So that's kind of what's going on in there. Then let's go to our printer and see how do we check some of these things now that we have an idea of what steps mean. So the printer, let's see if we can get to him. There he is. So the printer has stepper motors, one over here, one back in the back for the y-axis. There's one for the z-axis down, you can't really see, it's down in there. Like I said, the y has to move the most mass back and forth on this style printer, so it's the one that's most likely to skip a step if you're trying to move really fast or accelerate really quickly from one direction to another. It's the one that's most likely to skip. Another thing that can cause that is the belt slipping. So maybe the stepper did its job, but the belt that is moving everything actually skipped on the pulley. And in that case, you just need to tighten the belt up. But if you're seeing layer shifts, it has something to do with your machine doesn't actually know where it is at any time. It just knows where it's supposed to be. That's part of the reason for homing the thing. Let's go ahead and turn it on and home it, in fact. I did make some changes. Remember, I was trying to home, I was trying to do the automatic bed leveling, and it would try to send the bed too far forwards, and it couldn't move any further because it thought the bed was bigger than it really was. So I changed that in the firmware. In fact, let me see if I have that easy to look at. Yeah, it's right here. Right here in configuration.h. There's X and Y bed size. And the defaults in here were if you look at the specifications online, it says something like 235 or 230 millimeters or whatever. But if you put those numbers in here, it doesn't take into account the fact that, yes, the bed, if you measure it, is that big, but the print head can't actually get to all those places because of some other limit. It physically runs into something and it can't get all the way to the back. I'm at the limit here. There's something physically stopping it, and I can't actually print at the very back of this bed. So even though the print surface is large enough, the print nozzle can't actually get to all those places. So I changed those to 225 and 215. And now when I go to, let's go to home. No, not that. Home. It will not grind on anything, which is generally better. So that's an easy fix. Just going out and physically measuring where the nozzle can get to on the bed and going in. You might can change that on the printer itself in the little control panel over here. But I'm going to change, I did change that in the configuration.h. So I already changed that, and then just measured with a ruler. Just got out here and measured exactly how far it could go. Well, on the metric side. What else did I change? You want to check and make sure that if you tell the nozzle to move a certain distance, it actually moves that far. There's a couple of ways you can do that. You could get the nozzle to one spot somewhere and measure, tell it to go 50 millimeters and measure where it should end up. So that's one thing you could do. I actually went in, since I have the quick change thing over here, I just took it out and mounted it over here and put in one that had a pencil on it. Now I may have to adjust the pencil to the right height. Put a sheet of paper. Let me get oh, it's under the camera. I have to move you around a little bit. And let's tape that down so it doesn't slide around too bad. Now these X and Y steps are generally correct. They're generally not going to be something you need to calibrate, but it doesn't hurt to check just to make sure. Maybe you keep printing parts that don't fit together. Maybe somehow your X and Y steps got changed and they're not correct. I don't know, but generally they're going to be fine. So let's get this thing down where it's going to write on our paper. All right, so we got a thing, and we can just go to move. And I'm over here in the menu and move. I'm in 10 millimeter increments, and you could write G code to go and draw out a certain pattern, but most printers you don't have to even have the fancy touch screen. You can just do into move axis and move by 10 millimeter increments or 1 or 0.1. I'm going to use X. Let's do 50. So there I've got, let's see, probably kind of, there we go, you can see it. I've got a line that should be 50 millimeters long, and then you can get something that you trust to be relatively accurate, and it's exactly 50 millimeters. We could 50 millimeters that way, and we ended up exactly where we started. So it seems like that's 50. If you wanted to check, is your printer square, you would check this diagonal, right? So you have to remember some Pythagorean theorem. I don't know this number right here. So 50 squared plus 50 squared, that would be a squared. Let's see. Oh, it's on there. A squared plus b squared equals c squared. So let's see what c should be. Let's see, 50 squared plus 50 squared. So that line should be, so this is not, this is a, b, and c, not a squared, b squared, c squared. 70.71 across here. That, it is 70. And it certainly, with this accuracy of this ruler, I could totally believe that's 70.7, 70, almost 71 millimeters. So we could check across here also. And yeah, same thing. I think it's pretty well square. Now, if you got some other number, like you measured across here and it was 75 millimeters or something, then maybe you're printing the right lengths, but something about your mechanism is not square, and you're printing a shape more like exaggerated, but more like this. So you print 50, 50, 50, and 50, but they're not perpendicular to one another, and then this angle comes out way, or this distance comes out way bigger than it should. So to find this distance, let's get rid of these squares, they're bothering me. This distance is the square root of a squared plus b squared, would be that length. And so you can measure that to make sure it's square. You can also, if it looked like this, then you'd be pretty certain that it's not square. But it could be off a little bit and you might not notice it. It would be better to use calipers to measure this instead of a ruler, because you get, so these particular calipers will get down to 1/1000th of an inch, The only problem is they're in inches, so you have to go convert over to millimeters because all of this is in millimeters. That's what we're going to do in a second, but I haven't done that yet. I just used a ruler that already had millimeters on it. All right, so generally this is okay though. Generally this is not going to be your problem as far as calibrating. Same thing for Z. Obviously for Z you have to do something to make the Z axis move up. So maybe put some markings along the edge here and tell it to move up a certain height and make sure it did move up that high. So I kind of need the pencil, which is in here. So, oh, if you do something like this, remember the way we set ours up, we have the BL Touch mounted on the part that's removable. So that's fine. You just have to remember you can't home Z without that thing on there. Otherwise, there's nothing to trigger that it will stop. In fact, since I've built this, or I didn't design this quick change thing. You go to Thingiverse and do quick change Ender 3, and it's probably the first one that comes up there. I just like using it. So I think I will either go in and mount the BL Touch to the base itself, so that you always have the ability to probe. But I think actually what I'll do is, remember when we got down inside here and installed the BL Touch in the first place, there's two different ways to hook it up. One where it's just a probe for bed level, and the one that we have it hooked up, where it's the Z end stop and the probe. So I might go back and put the Z end stop back and set this to be in just a probe. I might go ahead and do that, not today, but that way if I do put another tool in here like the pencil or the laser or the little rotary cutter tool, that I'm not relying on this BL Touch, which is no longer mounted to do the Z height. So anyway, just remember that you can only home X and Y if you take your sensor off. All right, so let's see. Let's put a 50 millimeter mark. We'll just mark with this. I think I'll be able to see it. And actually, let's do 100. So it's, you don't want to do too small of a increment or distance, just because if you do too small, then you won't notice any small changes. All right, I know you can't at all see that mark, but I can barely see it. It is a black Sharpie on a black thing. But let's move. I think that was 3, 4. And it's pretty much perfect. Yeah, so I would not be worried about that going the wrong distance. I think that's perfectly fine. All right, so those are usually fine. Those are, unless you have loose belt problems and you're skipping movement all over the place or something like that, you're generally not going to have problems with any of this movement. But there is one that you can have problems with, and it affects your prints in a way that you may not even notice. Well, you can certainly notice the print being poor. You may not know why it's being poor. And that's the one called Esteps. So I actually need to get this filament out of here to do that. So let's hold up. Let's get this off. And let's heat our nozzle so we can get the filament out. I really do like this touch panel thing. Oh, and last time we ended, I was thinking that it wasn't working because I was pushing the stop. I didn't want to let it crash into it and not work, and it kept giving me this error. It was working all along. I forgot that when you home X or Y, well, let's do it. Let's home X while it's heating up. So it hits it twice, and I was forgetting that, and I only hit the thing once, and it was expecting that second hit. So it hits it, bounces off, and hits it again, kind of to get a second reading to make sure it's doing everything right. And I only hit it once, and it never got the second reading, and it was really confused on what was going on. Oh, I gotta release the steppers now. Don't remember how to do that on this. Let's see, I think it might be in settings, machine, custom, disable steppers, there we go. And so I only hit the one time, and it never got the second hit, and it was like, oh, something's wrong, it broke in halfway while I was homing. So that's why it was fine the whole time after we got the second firmware installed. All right, so what we're going to do now is called Esteps. These are extruder steps. So these are the ones that control how much filament is coming out and going down into your hot end. I think we're probably heated up enough that we can get our filament out. I just got to find where, I don't know where there's extrude. That's probably the one I want. Let's do a little bit. All right, so we loaded some, or we forced some to come out. Now I'm going to suck it back up in there. Maybe a little more. All right, so it's the problem with these tubes is you can't see inside there to know where the filament's at, but I'm pretty sure it's far enough out now. All right, so I want to cut all of this off to this nice clean, well actually, let's go ahead and do that, and then I'll cut it again. So like I said, these are the extruder steps, the E steps. I'm going to run them through the extruder, but I don't want them to go through the hot end. So I'm going to actually unplug or unscrew this part and just let it come out here. I can get it. All right, so there's coming out. Now I'm going to cut it flush right here. Let's turn this a little bit. So I'm going to pretty much cut it flush there. Now I'm going to tell it to extrude. It only, remember, your hot end has some protection on it that unless it is heated up, it won't extrude. Even though it's not going into the hot end, it thinks it is. So if the hot end's not heated up to an acceptable extrusion temperature, it won't do this. So you do have to heat the hot end. I'm going to tell it to come out 50 millimeters. So load 50. I think that was 50. And then it spits out what should be 50 millimeters of filament. This one I am going to measure with my calipers. Let me show you how you use calipers in case you don't know that. Now again, these are not metric. Let's see if I can get them the right way for you. This is a inch version of calipers. Maybe turn that off so it's not so reflective. All right, so first thing is you close them, and this dial can rotate, right? So you want to line up when they're closed. You want to line this up with 0, so that you're starting out. That's called zeroing or calibrating the calipers, and then you'll measure whatever it is you're going to measure. Let's say we're measuring this thing, and then you read. Let's see if we can get all of these numbers on here. Oh yeah, there we go. All right, so you read the inches from here. So this is 0 inches, 0.4, so 0.4, it's a little less than half an inch, and then you read the second and third decimal, so the hundreds and thousands place off of the dial. So I'm at 1, so this is actually 0.1, right? So 0.401 inches. So you can get down to a thousandth of an inch. Let's do another one that has an inch something. So here we're at 1 inch. There's a larger upper, it's in kind of a superscript. That's 1 inch, 1.2, and then off the dial you get 20. That's basically on the 20 mark, so 20. So 1.220 inches. Another one. Here we're at 1.5. It almost went to 6, but it didn't pass this mark for 6, so it's 5. 1.5. And then on the dial we have 46, so 1.546 inches. So you can get a lot of resolution out of calipers. Typically, you might find some calipers that are only down to 1/100th of an inch, but most of them you're going to find that are reasonable are going to go down to 1/1000th of an inch, and certainly they do make them in metric also. I don't have one. I don't actually like the digital ones. They're, you just line them up and it just spits out a number on the screen, which is fine, but invariably the batteries are always dead in mine, so they don't do anything then. So I actually like the manual ones. Let's go back to our printer. Where is he at? There's the filament coming out right there. All right, so we told it to spit out 50 millimeters of filament. So I've got to measure. Let's see. We'll measure. My hands are probably going to get all in the way, but all right. So that's how much I got right there. So let's go back over here and see what that actually relates to. So I got 2 point, and it didn't get to 1. It's almost to 1, but it didn't. 2.6 or 2.06 because there's a, it didn't get to 1. 2.06567 inches. Now we'll have to convert that over. There are 2.54 centimeters per inch, or well, 25.4 millimeters per inch, but we'll do it this way. There are 10 millimeters per centimeter. So that'll give us how many millimeters we got. 2.067 times 2.54 times 10. We actually got 52.5018 millimeters. We asked for 50 and we got 52.5. So what this would do is we spit out more filament than we wanted. So this is going to cause overextrusion. So you're going to have uneven surfaces. You're going to have little blobs maybe on the surface, but it's not going to create a nice surface finish. So we need to change this. We need to make this actually spit out 50 millimeters if we want 50 millimeters. Another thing that could happen here that I didn't look at is I haven't actually measured the diameter of this filament. I'm assuming that I'm spitting out 50 millimeters of 1.75 millimeter diameter filament. If the filament is bigger or smaller, then the 50 is also, it may not mean anything. If I've got 2 millimeter, it's not going to be this bad, but if I have 2 millimeter diameter filament and I spit out 50 millimeters, then I've way over extruded. I extruded the right length, but way more filament than I needed because it's so much bigger than what I needed. So you kind of have to do both. You have to measure the filament diameter, and this one is called the Esteps. So I need to calculate the correct Esteps. So I need to know what my current Esteps are. So I could find that over here. If I look up, is it called Esteps? I can't remember. I think it's just going to be in steps. Let's see if we can find it in here. Here they are. Default axis steps per unit. And then they say that X, Y, Z, and then E0. E0 is the first extruder, E1 is the second extruder, and so forth. So I'm currently at 103. These are the X, Y, and Z steps to move in the X, Y, or Z direction. Why the Z is so different is, remember, the X and Y axis are belt driven, and the Z axis actually has a threaded rod, a screw, that is driving it up and down. So that's why it's so different from the X and Y. So I'm at 103. So my current Esteps You can sometimes find this in the printer menu also. I know I could find it on this particular printer's menu, but with the SKR board and the touchscreen thing. But it's probably simpler to find it in the, I don't know. Sometimes they don't show it in the menu on the printer itself. So that's why I dug it out of the config. It's in configuration.h. Current Esteps is 103. All right, so if I take that 103, this is steps per millimeter, is what that is telling me. 103 steps per millimeter. So that's actually a lot of steps to go 1 little millimeter. I extruded, well, I wanted to extrude 50 millimeters. So my current E-steps times the desired amount of extrusion. If I divide that by the actual amount extruded, this 52.5018 millimeters, these millimeters will cancel out, and I'll have a new value here that should be smaller, right? I need fewer steps per millimeter in order to get, because I got too much extrusion. So this is current E-steps value. This is desired, I guess, extrusion. And this is the actual amount extruded. And this answer will be the amount of E-steps that I need. So let's see what that is. 103 times 50 divided by 52.5018. So I should need, according to this, 98.092. I don't know how many decimals I can actually put into the thing. Probably just 98.1 steps per millimeter. So I need fewer steps. Now you probably want to do this more than once, and maybe even more than 50 millimeters, maybe, because this one does need to be relatively accurate. So you probably need to do this a couple of different times to get the exact amount, and maybe, like I said, more than 100 or more than 50. Maybe do 100 and see how much you get. But let's go over here and put in 98.1. I could type that in here as the 103. I could type 98.092 and recompile and re-upload. But most printers will let you go in and change E-steps on the printer, and I can do that here. So let's get this off the screen and turn that where you might have a chance at looking at it the right way. So over here, I can go to settings, machine, and it's going to be, if you're in the plain Marlin, it'll be similar settings, and it might even have machine as an option. But there's steps per millimeter somewhere in there. Let's see if we can make that not glare. Maybe I can put it on the printer. It's going to be kind of a glare either way, huh? Maybe if we... It'll get darker, but at least the glare won't be there. So I'm looking for steps per millimeter, and you can see there's the numbers that are in the firmware: 80, 80, 400, and there's the 103. So I wanted it to be 98.092. All right, so it only let me use 2 decimals, so 98.09. It's there. It is not permanently saved yet. You have to go in and save it to the EEPROM. So how you do that on this particular thing is we go back to this custom and save to EEPROM. Now it should actually save. The way I had it, but without saving, it would work until I turned the printer off, and then it would go back to the 103 number. So you either have to go upload the new firmware with the 98.09 number, or you have to go in here and save it to the EEPROM. All right, So now we would go back and try again on our extrusion. Maybe we can lighten it up a little bit. So let's cut it off again here. And then let's go to move or extrude and load 50 more. And like I said, you probably should go to something bigger than 50, but we're just doing this to give you the idea of how to do it. So let's 0, still on 0, and then let's measure this guy. Now if it's curled up like that, you're not going to get a good measure, so that's kind of hard to do with all the stuff you have to hold at one time to get it straight here. Alright, so now we are at a different number, 1.94, and then it's right between the 3 and 4, so 9.435 inches. And then let's convert that over. 1.9435 times 25.4. That's a little under 49.4. So we're getting closer though. So we would need to, go a couple of more rounds. I would probably, in fact, I probably will, since it's off. Once we close down the video, I'll probably go down and extrude 100 millimeters of filament to try to get a little bit more accurate reading on what's going on. But that's the one that if you're going to change any of these things, probably it's the first one to check. Everybody, you post on a forum somewhere, they'll say, did you check your E-steps, or did you calibrate your E-steps? That's what they're talking about, is the number of steps that your extruder E is taking to extrude a certain amount of filament. And a lot of times it does vary machine to machine. So your firmware comes with the generic number, which is going to be close, but there is a decent chance that yours, for whatever reason, needs a slightly different number from what is coded into the firmware. And again, it does also happen to be affected by the actual diameter of the filament. Your slicer is assuming a certain diameter filament. 1.75 is the default assumption. And if your filament is thinner or thicker than that, then you're going to either under or over extrude, because your slicer is assuming a certain volume of filament flowing through the hot end. And that's how it determines how much to extrude, is based on that volume calculation. All right. So next time we'll do some more. Maybe I've got some more painting done by then. We probably don't need a lot to do on the printer. I'll go in and calculate these. I'll tell you the final number, what it was. It will not at all be useful to your printer unless you had, even if you had the exact same thing, you would need a different number. But just so you know what it ended up being, I'll tell you. And I think we'll be good to, on Wednesday. I think we're going to try and do some photogrammetry. So that's creating three-dimensional models using a camera. So like your cell phone camera, and some software that you can usually access for free. Some of it's paid, but there are some free versions. And it's pretty neat to do. So we'll see you on Wednesday with some new things.